All right, hopefully this goes without a hitch, but this is the first, and really the first and second lessons of Chapter 8, Integration Techniques, L'Hopital's Rule, and Improper Integrals. I say first and second section because as we look at the first section, you can see that it's only one slide because it's dedicated to the use of previous rules that we've already discussed and when and what to look out for, when to apply them and what to look out for. I usually do this with a packet in class, so I'm going to wait on this, do this together when we return, even when we return, and then we'll talk about that more fully later. But I'm going to move on to integration by parts. And I'm just going to read through it with you. I've got my book open to reference if need be, and we're good to go. All right, it says, in this section you will study an important integration technique called integration by parts. This technique can be applied to a wide variety of functions and is particularly useful for integrands involving products of algebraic and transcendental functions. For instance, here are a couple examples, okay, of things to look out for. Basically, if I was to rephrase this, I would say it's a mix of types of functions. X would be considered an algebraic function, x squared, so on. You've got sine x, that would be considered a trigonometric function. E to the x is a transcendental. So a mix of these types of functions put together, and separation by, or integration by parts, is the formula or is the process we would use to solve that. So here's where it's birthed from. It says, suppose we have a product, and when you take the derivative of the product with respect to x, it would be the first times the derivative of the second, plus the second times the derivative of the first. Or you might have seen that in a different order, v times du over dx, or plus u times dv over dx. That's fine because the commutative property still holds. It says where both u, I apologize for that, u and v are differentiable functions of x. When u prime and v prime, or the derivatives of u and v, are continuous, you can integrate both sides of this equation to obtain the following. So here's what we have. If I integrate all three of those pieces, then what I'm looking at is uv equaling the integral of u dv dx plus v du dx. And basically, if you treat these dx's as actual numeric amounts, they would cross out, giving you the u dv and the v du. Now, why is this important? Well, we're going to approach integrations or integrands that we're not going to be able to solve as we did before, and they're going to be of the form integral of u dv. It's going to be a mix of things that we can't separate, we can't integrate in a way that we already know how. So what's going to happen, and I have to put in an integral sign here, we're going to be able to replace the integral of u dv with the product of uv minus the integral of v du. Now I'm hoping that one of your questions that you're thinking of right now is, well, what's u and what's v? And that's where we're going to be practicing, or that's what we're going to be practicing during this lesson. How to identify what is u, what is v, and what are the du's and dv's that show up in the process as well. They all do have a specific spot or a specific position. So we're going to jump right into the integral of x, natural log of x, dx. It says, let dv be the most complicated part of the integrand, and u is what remains. Now, this is a general guideline. It might not always be the way that it's going to be solved, but that's certainly what we're going to start with. So if you look at the integrand, okay, that's this, and we have to identify what is most complicated of the two, I would assume that you would say the natural log of x is more complicated than x. It's more complex. It has different parts and things to be mindful of, where x seems to be pretty simple. We just have to apply the power rule to its derivative or to its integral. It's not really anything to be super concerned about. So if we let dv be the most complicated part, then dv would also have to include this dx. So down here, dv is going to be natural log of x dx. Okay? That means This is of the form the integral of u dv, and this part has already been taken for dv, that leaves x to be u. Okay? Let u be the portion that results in a simpler du. Now these are two separate types of guidelines, but usually they go hand in hand. While you figure this out, it's also important to figure out their counterparts. So u's counterpart is du. Du would be equivalent to dx. Okay? But look back up here. If this formula is equal to uv, well, we've got u. I don't have a v. Can I figure out v? Do we know what the integral of natural log of x is? And I don't. So there's a trial that actually did not work. If it doesn't work, and in this case it did not work, we go on to the second guideline. Let u be something that has a derivative that actually looks simpler than it did before. All right, well, what if ln of x is the u and dv is the x dx? If that's the case, then du would be 1 over x dx. And if I integrated this,
plus c. Okay, so why does that matter? Well, if I can separate it like this, then I'm saying that the integral of u dv is equal to uv minus the integral of v du. Well, then that means for this problem, u times v is the natural log of x times x squared over 2. I'll include the plus c later. Minus the integral of v du. Is the result here integrable? And the answer to that would be yes. I can actually take the integral of this portion now. I can simplify it to look like, I'm just going to write this all together a little bit differently. Right? 2x's here and x here can cancel to just one x in the top. And I took 1/2 and I brought it out front. Final answer, and I apologize for not having the room for it. I wrote this different all 3 times. It doesn't matter. Minus 1/2, and the integral of x would be x squared over 2 plus c. This, if you want to leave off the plus c up here, you certainly can. We eventually get a plus c regardless. I could simplify this a step further, but for lack of space, I'm going to leave it alone. And I now have an antiderivative to something I was not able to integrate before. Okay, so let's run through that one more time. If letting dv be the most complicated part doesn't lead you to a better or a solvable integral, then move on and let u be the portion that results in a simpler du. There is a way to look at this in a more easily understood way, and we'll get to that later in the lesson, but for right now, that's what we're doing. Then once you assign u and dv, figure out their counterparts, and plug them back into the formula. That's it. That's the whole lesson. All right, so down here, step 1 was to allow dv to be the most complicated part. So of this, what would be the most complicated part? And I would assume that you would say dv would be the e to the x dx. Well, this question has kind of been laid out for you, so let's go with what's being suggested. If we let u equal x, then dv would be the rest, e to the x dx. If we let u be the e to the x, then the dv would be the x dx. It's whatever is left over.
If u was 1, which there'd be no point of that because the dv would be everything else, and if I could have integrated that to begin with, I would have. And if I let u be the entire integrand, then dv would just be the dx portion, okay? So there's tons of ways to figure this same suggestion, to figure out the same integral, and not all of these ways are going to benefit you, so we're going to have to be creative. Sometimes we might mess up and have to start over, and that's okay. So before we continue, there's not space to actually solve this, but let's talk about what the benefits of these would be. If this was u and that was dv, then du would be dx, and v would be the integral of this, which is e to the x plus c. That means that I could trade my integral for the combination of uv minus the integral of v du. Is that solvable? And the answer would be yes. So this is my preference right here. But I do want to look at the others to see how that does help or hurt the integrand right from the beginning. If u is e to the x, then the corresponding du would be e to the x dx. If v or dv is x dx, then v, the integral of that, would be x squared over 2. That means that I would trade this integral for the combination of uv minus the integral of v du. Well, here's a problem. This is more complicated than what we started with. We're actually worse off because our x is growing. So I would definitely not recommend this direction. If u was 1, then du would be, well, what's the derivative of 1? It would just be 0, right? And v would be the integral of this, which I don't know right from the beginning. So again, bad choice. If u was this, then du would be, according to the product rule, I'm going to try and remember the way that you guys have been taught this. So it'd be the derivative of the first times the second plus the second's derivative times the first. Now I learned it as the first times the derivative of the second plus the second times the derivative of the first. Oh, and I forgot my dx in here. V would be the integral of dx, which is just x. Therefore, I would trade all of this in for the combination of uv minus the integral of v du. Can you see how this is more complicated than what we started with? We don't want to go any more complicated. We want to stick to something that is solvable and settle there. Finally, we would integrate this, and you would have for a final answer x e to the x minus e to the x plus c. A solvable antiderivative from something we couldn't break apart as is. Okay, so keep up that mentality. Remember, and I'm going to write this at the top of every single one of these pages till we have it memorized. We're learning that the integral of a u-dv combination that we can't solve as is equal to uv minus the integral of v du. So in order to solve this, you have to assign the proper u and dv, find their corresponding du and v, because du and v are part of what we need for our answer. Okay. Is there a specific way to determine which portion of the integrand should be u and or dv? Now I gave you 2 guidelines to use as you go through this process, but sometimes those guidelines aren't foolproof. So here's another thing to consider, and it's the acronym LEAT. This is an appropriate way to assign u, or at least it's a great first attempt in assigning u. So if you have a natural log piece, let that be the u right away, because we know its corresponding du is going to be 1 over x, and 1 over x is easier to look at. It's easier to manipulate than the natural log of u. If there is no logarithmic piece and you have an I, now of course I'm going to have to look in because my brain's not working just yet. I have it here somewhere. It's not binary. Is it inverse trig maybe? I thought it was right there in front of me. Of course, I'm giving you notes from the first copy that I did these from, and oh, there it is. Okay. Yes, inverse trig. So if there's an inverse trig part, arc sine, arc cosine, whatever, assign that to your u, because we know that the derivative of that, again, turns into something that is algebraic and something we can manipulate, but taking the integral as is becomes much more complicated. Followed by A. A stands for your algebraic part. Okay? Algebraic being any sort of manipulation of x, any sort of morphing of x, whether it's just, linear or quadratic or anything along those lines. T stands for trigonometric. And E stands for exponential. Well, why would exponential be your last choice for u? Well, because it's so easy to manipulate, it could easily be your u or your dv, because we could take the derivative or the integral of it very easily. So this one is the most mobile, I guess you could say, or the most easy to integrate, or whatever. And trig tends to be pretty straightforward as well. You go from a sine to a cosine and a cosine to a sine, whether it's a derivative or an integral, very easily. All right, so let's see this in action. You have 5 choices for your u in that appropriate order. So I look at my next integrand. I know I can't solve it as is. There's no u sub that's appropriate for this. And don't confuse integration by parts with u sub. Although we are assigning u, it's not the u sub that we're traditionally used to. All right, so do I have a logarithmic piece? Or better yet, what do I have? So I have 2 pieces that are considerably different. The first piece would be considered algebraic, x squared. Sine x would be considered trig. Now, of algebraic and trig, which one comes first in the LEAT acronym? And the answer would be algebraic. If that's the case, assign u the algebraic piece and assign dv the next part. The u is going to be differentiated, but the dv is going to be integrated. So this can actually hurt your brain a little bit. You're going forward thinking in one of these and backward thinking in the other. So make sure that you are using the appropriate rules when you come to them. U is x squared. Its derivative would be 2x dx. dv is sine x. Now imagine yourself taking the integral of sine. And I know that you guys have like a little code that you'll write off to the side. I don't know what your code looks like, but this is the code that I'm thinking of off the top of my head. I know for a fact that that one is the first one. Therefore, the rest of these become a little bit easier to fill in. Of course, these S's are not the same S's. It's just helping me figure out what to put in the blanks. Okay. So the integral of sine, moving backward, would have to be negative cosine. All right, so if this is equivalent to the integral of u dv, then it is equal to the combination of uv minus the integral of v du. I guess I don't need the parentheses here. Put it here instead. Bring this out.
clean it up a little bit, and this is what I have. Negative x squared cosine x plus the integral of 2x cosine x dx. And actually I can bring the 2 out as well. Now this is still not separable and able to be figured out the way that we're traditionally used to, but can you agree that it's a simpler integrand than what we started with? This one has just x to the first power, this one has x to the second power. So what we did worked, we just need to do it again. All right, so reassign. U is going to be the algebraic piece. dv is going to be the rest. du is the derivative of x, which is dx, and v is the integral of cosine. Here's cosine, moving backwards would be sine. Alright, so I have my original x squared cosine x, and then I have a plus 2 times what I get from this new combination of uv minus the integral of v du. I know the integral of sine, so I'm able to actually figure this out in full in one more step. I'm going to distribute this 2. I get 2x sine x. This 2 also comes in front of that. And the integral of sine would be negative cosine. So I'm going to change this right away, this negative, to a positive, and finish up my integral. Alright, all because we are assigning the appropriate u and v. Remember, Liate, it is going to be the golden rule when it comes to solving these integrals. Keep going. I'm going to write the formula up at the top so we don't forget it. The integral of u dv is equal to uv minus the integral of v du. I'm also going to write Liate off to the side, and maybe, well, I don't have any trig up here, so I won't worry about that just yet. All right, Liate helps us assign the u, at least a first attempt at assigning the u. So I do have a logarithmic part. That is going to be my u. And I'm going to actually, I'll just keep it up the way I'm going. dv is what's remaining. You're going to have to figure out du and v as well. So I'm going to pause, make sure that you guys get some time to try this on your own. Certainly you could pause the video so it wouldn't be an awkward amount of length, I suppose. Alright. du is the derivative of u. In this case it's 1 over x dx. And v would be the integral of this. So integrals mean that your exponent goes up, and that becomes your denominator as well. That means that my u dv combination is equivalent to u times v. I'm going to write it in an order I'm used to seeing it. You don't have to. You can keep it in the order that you had it before, but I just didn't want this x to be touching that x to the 6th, and I wanted to avoid parentheses, but whatever. All right. Minus the integral of v times du. Hopefully you see that this 6 can be pulled out, and these x's can be simplified to just x to the 5th. I'm going to clean it up before I actually solve it. Alright, final answer. X to the 6th, natural log of 6, or natural log of x over 6, minus 1/6 times x to the 6th over 6 plus c. Certainly I could take a step to combine the 6 and the 6 to make a 36, but I'm going to save some time and just leave it as is because of my lack of space. Please, on your part, simplify that further, especially in a testing situation. Okay. Again, I'm going to write the reminder off to the side. U and V, what do I have here? I don't have log. Do I have inverse trig? And I do. So I'm going to say start because we don't know if this is going to turn out correctly or not. We might have to do it a couple times, and that's okay. But I'm going to start by saying that U is arctan of x. That means dV is the remaining portion. The corresponding du is the derivative of arctan. Hopefully you remember it. If you don't, it's 1 over 1 plus u squared, in this case x, dx. The derivative of x is just 1, so I'm going to write dx. And then if dx is my dv, v is the integral of that, which would just be x. I'm going to give you a second to fill in the blanks of uv minus the integral of v du. And hopefully you have that. Again, my order is okay based on the commutative property, but I choose to put my algebraic part in front so that the x's don't touch or need parentheses. Minus the integral of v du. All right, can you look ahead to see what's going to happen here? My denominator is 1 plus x squared. My numerator is now x. Since x squared and x differ by a degree of 1, then this is just going to be a traditional u sub. A u sub that needs the balancing. So 2 goes in, 1/2 comes out. And my final answer, well, I guess I shouldn't do my final answer. Let me remind you that this now says, with the 1/2 out front, that part has become 1 over u du. Okay, so as I integrate that, just remember that that's where my mind is while I'm integrating. I've got x arctan of x minus 1/2 of the integral of 1 over u du, which is the natural log of u plus c. Now why wouldn't I put absolute values around this? Well, 1 plus x squared is a quadratic function that is above the x-axis. It's transformed 1 unit higher. So I know that it's never going to be negative anyway. There's no need for the absolute value. Okay? We're almost there. You saw in the last example, let me straighten this out. You saw in the last example the need for repeated use of integration by parts. So this was done actually out of order. The last example I'm referring to is x squared sine x, where we had to do it once and then we had to do this again. So let me reference that a little bit differently. You saw in one of the last examples the need for the repeated use of integration by parts. In such cases, the tabular method may help organize your workspace. Tabular is just a fancy way of saying use a table that's going to organize your thoughts. And in this case, I'd like to show a similar question like we had before, but using this tabular method. The tabular method becomes very helpful when we have things of the form like x to the n, meaning you're going to see a repeated use of that x as your u, and each time it becomes a simpler du, so eventually you're going to get to the right answer, but you don't know how far along that process is. Or maybe you can guess, but it's going to take a while. Same thing here, and same thing here, okay? So the tabular method is going to look like this. We are going to have u and dv assigned, okay? The first, actually, and I should have written it already, but the first column is for a plus or minus, because if you remember, every time we do this process,
There's a minus in the process, which every time you integrate, especially if you think of a trig function like cosine and sine, you know, you're bouncing back and forth from positives and negatives. If you include that with a negative that's already there, the sign is going to be changing anyway. Like if you take an integral and then you have to take an integral again, and in front of it there's a negative, those two negatives are going to become a positive. So the alternating signs are going to have to be accounted for. We will always start with whatever sign is attached to the u or dv, the u that we're choosing. So again, following Leate, I have x to the fifth and sine 2x. Sine 2x would be trig, x to the fifth would be algebraic. So x to the fifth is my u, and du would be sine 2x. Okay? This is a positive integrand. All right, I'm going to fill this table out as far as I need to until this becomes 0. That's going to be my clue to stop. So the derivative of x to the fifth is 5x to the fourth, then 20x cubed, followed by 60x squared, 120x, 120, and then 0. So here's what I already know. If I was to use integration by parts the way that we have been, I would have to assign u however many times, and it would be an incredibly long process. Instead, I can organize my thoughts in this way, and it's relatively easy. These are going to alternate. Okay. And the sine 2x needs to be integrated. Now, if you're not sure what that's going to look like, then just integrate one of the sine 2x's off to the side just to see what the pattern's going to be. And there will be patterns involved. Okay, if this is the case, I'm doing a traditional u sub where 2x would be my u and du would be 2 dx. That means I'd have to throw in a 2 and I'd end up with a 1/2. And the answer would be, if you remember our trig functions, negative 1/2 cosine 2x. I'll worry about this plus c later, but for right now, it's going to be negative 1/2 cosine 2x. Now imagine yourself integrating it again. I'm going to cover this up for a second. The integral of cosine 2x, u would be 2x, du would be 2. You'd have a 2 and a 1/2 out front. All right, so I already know that I have a 1/2 with the negative 1/2 that's already here. Okay, keep that in mind. What's the integral of cosine? Well, the integral of cosine is regular sine, with the 1/2 out front, with the negative 1/2 that was already there. All right, keep going. We know there's going to be a 1/2. We already know the integral of sine 2x is going to be cosine 2x. Okay, now imagine this with a negative 1/2 in front of it. Okay, integrate cosine, you're going to end up with sine, which means there will be no sign change, but there'll be a 1/2 that you had to balance it with. Integrate sine, there's going to be a negative involved. It's also going to have a negative 1 or a 1/2 with it. Integrate cosine, you get sine, and imagine putting the 1/2 to balance your u sub with the negative 1/32 that's already there. Okay, and this is what you get. You do as many integrals as you need to, or antiderivatives. Here's how the tabular method evidently, this is how it eventually works. I want you to make arrows that go from the left column to the middle column. But while we assign each of these x's, we are also, or each of these u's, we're also integrating. So once I integrate, I end up with this answer. All right, so your middle column will actually jump down a column. Now what happens when I get to 0? Well, I'm not going to integrate anymore because that 0 is actually going to be represented with your plus c at the very end of the problem. Okay? Here's what the final answer looks like, and I apologize, it's going to take a couple rows. X to the fifth times this becomes negative x to the 5th over 2 cosine 2x. Now combine these together. It's a negative with another negative. It's a 5 with a 1/4 sine 2x. Next setup, positive 20 over 8. I'll simplify later, but 20x cubed over 8 cosine 2x. Follow this one. It's got one negative between them. Negative 60x squared over 16 sine 2x. Okay, follow this one. Positive 120 with a negative 32, or negative 1 over 32. So that'd be a negative 120x over 32 cosine 2x. Now we've got another negative 120 with a negative 1 over 64. That becomes a positive 120 over 64 sine 2x. And then this final plus 0 is represented by your plus c. Now, of course, I would want an answer that was simplified a little bit further. 60 and 16 could be, let's see, that's 4 and 15 fourths. 120 over 32, of course, off the top of my head, that becomes 60 and 16, which again is 15 over 4. And 120 over 64 would be like 60 over 32, which would be 30 over 16, which would be 15 over 8. And I would clean this up and write it in one line. Notice that the signs alternate every 2. Notice that you see a progression between cosine and sine alternating back and forth as well. And notice that your coefficient is steadily being multiplied by 1/2, as we expected it to do in the first place. At least 1/2. It's also got the 5 and whatnots, but this is actually not the original way. This is the tabular method, so I did this a little bit backwards. This probably seemed overwhelming. You'll likely only have maybe 3 columns when you're doing your assignments, okay? But what would this look like if we tried to do it the original way? So switch these up. If I wanted to do this the original way, u would be my x to the 5th, dv would be my sine 2x dx. du would be 5x to the 4th dx. And v, we already figured this out, would be negative 1/2 cosine 2x. Okay? That being said, one time through this process would give me u v minus the integral of v du. All right, here's what I noticed. If I clean this up, then I now have positive 5/2 integral of x to the 4th cosine 2x dx. It looks better than it did, but it still looks like we're not quite where we need to be. So we reassign. Balance with a 1/2, this becomes, whoops, v is equal to 1/2 sine 2x. All right, no big deal. I'm just filling in the blanks. I can handle this, right? Don't forget that that's 5/2 times this entire answer. Well, how can that complicate things? Well, it will very quickly. If you don't take an extra step to clean up every line, you might actually end up with a big old set of parentheses, and I don't recommend that in the least. Alright, so let me clean up what I have in front of me. This becomes 5x to the 4th over 4 sine 2x. But don't forget that this is also, well, 2 x's. I don't want you to confuse by putting them outside, but don't forget that this 5/2 is being distributed to both pieces. So this 5/2 plus the minus 1/2 and the 4th, well, that 4, 2 can come out. This becomes a minus 5 integral of x cubed sine 2x. Again, looks better than it did, but are we anywhere close to being done yet? And the answer is no, and look how much room we've already used. So I'm just going to do dot, 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 and emphasize the fact that tabular was much more preferred in this instance. All right, so there is your integration by parts. A quick recap: make sure that you assign your u and your dv, most likely according to the Lie acronym, and fill in the blanks from there. The integral of u dv is equal to uv minus the integral of v du.